Welcome to the lectures on modern digital communication techniques. So, we have seen the different modulation techniques till now, and in the previous lecture we have mentioned that we have more or less covered some of the important modulating structures or the formats or generic representation by which you should be able to handle most of the modulations that we encounter, and of course there could be something beyond that, but whatever framework we have started off with should equip you with sufficient capability to be able to handle modulation schemes in the format or in the generic form that we have been working with. And while doing these things, in the last few lectures we have specifically stated that these signals which we are doing, which we are calling as memoryless, are having some problems which are overcome with respect when we are introducing memory. And the way we explained this was we took the example of QPSK. Then we said that in QPSK you would generally have the phases changing at every signaling interval, where if both the bits, that means there are two bits in QPSK, the quaternary phase shift keying, that if both the bits change simultaneously and you have no control on that because it is from the incoming source, since one of the bits is going to the I channel, the other bit going to the Q channel, it could highly happen that overall there is a 180-degree phase shift. Now, this drastic phase shift happening within a very short interval, that is the switching period from one symbol to another, which is very short, could give rise to zero crossing, and there could be spectral regrowth and all kinds of problems. So, one would typically like to reduce these kind of phase changes. So, we introduced the offset QPSK, where we said that let one of the bits change per symbol interval, and in that case when you change one of the bits, at most you can change by pi by 2 and not pi, and this would reduce the delta phi, that means the amount of phase shift that you are going to encounter, and hence the frequency growth should be less. And so it will at least it will give you resilience against zero crossing and envelope fading and all kinds of things. And then we also saw that there is another modulation technique which is the binary FSK, which could also be represented in the form of an offset QPSK, where the pulse shaping is kind of half sinusoid. And there also there is offset between the two I and Q channels. The I is used to modulate the cosine and the Q is used to modulate the sine, and by virtue of maintaining the sinusoidal pulse shape compared to a rectangular pulse shape in the earlier two, we would find phase continuity. We had also hand drawn the waveform structure, which is highly instructive to generate the waveform using some programming language, and you could easily see the waveforms that you would encounter in such a system. So, what we thought is probably it is wise to look at the power spectral densities or the spectral characteristics of signals before we conclude our discussion on modulation techniques and before we move on to the receiver structures. So, we begin our discussion today by looking at the spectral characteristics of digitally modulated signals. So, this is what is our main interest today. So, when we talk about channels, we have been saying since the beginning that channels are all kinds of systems through which the signal propagates, and generally these channels are band pass channels. So, it allows a certain set of frequencies to go through and it does not allow certain set of frequencies to go through. So, usually channels are frequency selective. So, we therefore have that generally channels are limited in bandwidth, right. So, that means they do not have a bandwidth which is spanning from minus infinity to infinity, and that would leave the system designer to choose the modulation technique considering channel constraints. So, we are basically getting into design aspects slowly. So, till now we have been writing the expression of the transmitted signal, we have been discussing in a bit of qualitative form about the spectral characteristics, this being more or less. What we aim to do today is to take a few steps forward in trying to more or less concretize this particular aspect. And why we want to do this The reason is that you would like to design a communication system, and that is what we had started off in the beginning as the goal of the course. So, if you have to design a communication system, the moment we talk about design, we talk about choosing parameter values, because parameter values are the ones which are the outcome of a design procedure. So, when the channels are limited in bandwidth, in that case the designer, that means you, are supposed to consider modulation schemes which would allow the signal to go through the channel by conforming to the constraints. So, for example, we will see sometime later that QPSK has a certain spectrum compared to the spectrum of MSK, and depending upon situation you would like to choose a particular modulation scheme over the other. So, one has to determine the spectral content of the digitally modulated signal, because once you know the spectral content of the modulated signal, then you would know that whether this spectral content would satisfy the channel constraint. So, what we will do today is try to look at the spectral content of digitally modulated signals. About the channel we will not do much, because we will simply state that if we can calculate this, we will choose that modulation technique which would satisfy the constraint of the channel. So, of course, that can be taken with examples. So, now the next important thing to be noted here is the information sequence that we have, that means the bit stream 1s and 0s, and which gets translated to INs, that means the amplitude values, is random. I mean, this we have been discussing for quite some time, and this is not new for us, that the source, if it is not random, then there is no point in communicating. That is what we have been stating since beginning, and the randomness that we have been stating would mean that it is not known a priori about what is going to be sent, although you have your fixed options. So, the example that we can take, the basic, the most simple example that we can take is the tossing of a coin. So, we know that the outcome will be a head or a tail. So, there is no doubt about that, it will be either a head or a tail, but what we do not know is what is the particular outcome in a particular tossing of a coin, right. So, that means the bits that are going to come, we know for sure they will be either taking the value of 0 or taking the value of 1, but we do not know which particular value they are going to take at this instant of time, and that is the information content that is being carried by that. So, that is what we have, that the information sequence is random, and hence since this random sequence is used to modulate a signal, and we also have this information sequence digital. So, again just a word of reminder that we said initially that if at all there can be communication from the source to the destination or from the transmitter to the receiver, you can do it through binary interface. So, that is what is the premise which we started off with. So, back to that same thing. So, basically using whatever we have stated before, that we are talking about digitally modulated signal, the modulation has been an outcome of this information sequence which is random. So, that means this digitally modulated signal is a stochastic process. So, that means it is a random variable which is a function of time, and what we are interested in is the spectral characteristics. So, if you have to study the spectral characteristics, you have to look at the power spectral density, right. Otherwise, you would have looked at the Fourier transform of the signal and you have got it. So, now since we have this stochastic process to study spectral characteristics, you generally look at the power spectral density, right. And again a reminder, so that things become easier as we do in this particular discussion, we did study the spectral properties of a narrowband stochastic process in one of the earlier lectures, and when we did that, the example that we took was for noise, and if you would recall, we wrote the signal model which was very similar to that of a signal. However, we said that it is random, that is it, that is the difference. The previous one was deterministic in case of signal, whereas for a stochastic process the expression looks the same, but it is not deterministic, it is random, that is what we stated. And then we said that we want to study the spectral characteristics. So, what we did, if you would remember closely, we did study the autocorrelation function of the stochastic process, and then a Fourier transform of that yielded the power spectral density. So, that is the same procedure of what we are going to take. So, let us take the power spectra of a linearly modulated signal. So, initially we will begin with a linearly modulated signal, and our typical representation of a linearly modulated signal would be S of t is equal to real part of some V t e to the power of j 2 pi f c t. The closest expression which you would have was we used V t to represent the low pass equivalent for Emery FSK in a few lectures back, and just to match with whatever we have learned before, V t was AM times G t for pulse amplitude modulation, and V t was I won't write it here, it is AM GT, and in case of QPSK in case of PSK you had Vt to be equal to e to the power of j theta m, and where theta m was pi multiplied by small m minus 1 divided by capital M, and for AM for pulse amplitude we had 2 small m minus 1 minus capital M, the whole thing multiplied by d. So, times Gt of course. So, that was Vt in these two cases. In case of FSK we had Vt as e to the power of j 2 pi m multiplied by delta f, and in case of continuous phase we had the integration of dt, and dt was I n g t minus n t. So, that is how we had these kind of expressions, and if you look at this expression it is definitely a real part of V t. If this is already real, no problem, times cos 2 pi f c t. So, that is the standard form which we are quite used to. So, as we said that we are interested in the autocorrelation function. So, we will take this autocorrelation function of S of t, because this is the stochastic process, that is what we have said, because V t is an outcome of the information sequence, and hence if this is stochastic, this also is stochastic process. So, the relationship of the autocorrelation function of the pass band to that of the base band was also established in our discussion when we studied the narrow band stochastic process. So, we had derived in details the relationship between the pass band and the low pass equivalent representation of the autocorrelation function, and we did identify that the autocorrelation function expression looks very similar to the relationship of the low pass equivalent representation of the signal and its corresponding pass band. So, for the signals, whatever relationships we have for the signal to the pass band from low pass to band pass, we have similar relationship for the autocorrelation for the narrow band stochastic process, and the equivalent representation of that as well as the band pass of that. So, if we are interested in the power spectral density, we will represent it as phi SS of f, SS because autocorrelation of S and S. So, power spectral density because of autocorrelation, so it is S, and tau gets translated to f because from the delay domain we are going to the frequency domain, and this is basically the Fourier transform of this. So, that is the relationship I have already told you before. So, this one going by this expression, you have also done a similar thing before, where real, if you have real part of something, you have the phi V v, which is the power spectral density of the low pass equivalent, and this is the other term in the negative frequency. Generally there is this complex if there is a complex. So, for certain cases we did find that this we do not need the complex representation. So, of course, what we have in this expression we had before, only thing is we are using the notations which are related to the signals. So, since the signals are now random signals. So, we have the pass band spectral properties connected to this power spectral density of the low pass equivalent process. So, what we can take from this is that in order to study the spectral properties of the signal, all we need to do is to study the spectral properties of the low pass equivalent signal, right, of the low pass equivalent signal. So, if we can study the power spectral density of V, then we could easily translate that to the power spectral density of S, where V and S are the low pass equivalent and the corresponding band pass signal. So, that is what is stated in this line. It is sufficient to determine phi VV of F, and these are not new to us. We have been using this since the time we have discussed the power spectral density of narrowband stochastic process. So, we look at Vt, and so just because we have discussed this, so therefore, we need to find phi Vv. In order to find this, we will start off with the expression of V, because in this expression we do not have the expression of V, it is expression of S in terms of V, right. So, moving further, let us consider a V which is in this form. So, as it appears, this form, this is kind of a pulse amplitude modulation, you can think of it in this way, and the information rate is of course 1 upon t, where t is the symbol duration, which is also the notation used here, and this is r by k, where r is equal to 1 upon T b. That means, this is equal to 1 by k multiplied by T b. So, that means, t is equal to k multiplied by T b. So, all these notations are which we are used to, this is not new to us. So, that is why I am proceeding in form of already prior written expressions. So, in case of PAM, In is real, which we have already seen, whereas in case of PSK and QAM, it can be complex valued, and well, you could easily separate them into the I channel and Q channel, and you could write it as I n G something and plus J times I of something else with G of t minus 2 n t and things like that. And you have already seen such an expression when we did study MSK. So, this is also not new to you. So, if we have to take the autocorrelation of V, we will directly write phi Vv. We have already defined this, so we are not going to redefine these expressions. So, you should be now familiar with the way we are writing these expressions. So, we have phi Vv of t plus tau and t, right, and which is half expectation of V of t conjugate times V of t plus tau. This is from standard definition. So, when we have expectation operation, we do need the PDF, the joint PDF, in order to compute this. So, let us see how we proceed with that. So, this expression we should now expand. So, V of t is what we have over here, a conjugate would lead to a conjugate over there, G is a real valued signal that we have already said since the beginning, and V of t plus tau should have V of t plus tau as another signal, and in that second signal we should have different index. So, I k and this expression. So, when we write it down, in terms of this kind of expression, what we have is half summation, this summation n equals minus infinity to infinity I n g t minus n t, and there is a second summation k equals to minus infinity to infinity I n plus k. So, we have something shifted with respect to this, because it is shifted with respect to this, and we have g t plus tau minus k t following this expression, right. So, this follows by using this expression in this, you will get there. Now, since you have the E operation, E will not operate on G, because G is a deterministic signal, G is the pulse shape, unless we are choosing this randomly. So, E would operate on this information sequence. So, I n is the information sequence. So, what we see is the autocorrelation is finally dependent upon the autocorrelation of the information sequence. So, it may be okay to assume I n, that is the information sequence, to be Whiteson stationary. So, by Whiteson stationary, what we mean is that the mean is not varying with time, and the correlation is dependent only on the time lag and not on the function of time. That means, the correlation and the mean will remain the same at whatever instant of time you are trying to calculate these values. So, we are also saying that there is a mean which is mu of I, and the autocorrelation would be given by phi IIM. So, we are using phi for autocorrelation, and this is naturally the expression. So, all we are trying to remind here is that we will be replacing this expression over here, right. So, we have still not calculated it, we have still left it in terms of notation, calculations will follow. So, now if you would expand this expression, we are going to get phi v v t plus tau t, that is the same expression here. We have n, we have k, and here we have simply replaced phi I k minus n as per the relationships over here. So, if you would work out these relationships, you are going to get this expression here, these two terms remain as it is, and then you could replace, let m is equal to k minus n, which is the difference between these two indices, and you could write the expression as phi I of m equals to minus infinity to infinity, and this is the index of n, because, and that is how you are going to get the expression, right. So, this would be a typical expansion of phi v v of t plus tau and t. So, this appears to be a bit cumbersome, but if you replace the terms, you would come across the expression which looks in this form, right. We are simply expanding the particular expressions. So, if you look at this expression down below, of course, we have this expression to evaluate. So, we will stop for a while and we will continue to evaluate first this expression. Once we have done with this expression, then we may take a look at what is the influence of phi I of m. So, as a first step, let us look at the second part in the summation, n equals to minus infinity to infinity, and this particular sequence. Gt is the pulse shape. Pulse shape means it could be the rectangular pulse shape which keeps occurring with time. It could be the raised cosine pulse shape. We had given you the raised cosine pulse shape. So, this keeps on repeating at intervals of symbol duration, which is capital T. So, and hence from intuitive guesses, you could clearly see that it is periodic, or you could also prove it based on the expression that you have of Gt. So, you have seen different Gt's, you have seen half sinusoids, you have seen raised cosine, you have seen rectangular. So, if you would try to put the value of t equals to small t plus some k times capital T, you would find that all these g of t's are equal to each other, and then you could easily see that they are periodic. So, if they are periodic, that means you would also claim that this, which is the left hand side, is also periodic with period t, because it is a function of this and that is periodic, therefore, this itself is periodic. So, that being periodic, what it effectively means is that phi v v t plus tau, if you add t with that and if you add t with this is independent of capital T. That means, after t it gets back to its original value, right. And of course, the mean value would be, if you see v of t was equal to I n g t. Now, expectation of I n was mu I, we had already pointed out, and you have this, and again this thing is periodic with t. So, that clearly shows that this thing is periodic, this is the mean is also periodic with t, right. So, what we see is that V t is a stochastic process with a periodic mean and a correlation function, right, which is also periodic. So, we have seen the correlation function is periodic, the mean is also periodic. Now, so what we have is a cyclostationary process, right. So, since we have a cyclostationary process, what we need to do is in order to calculate the power spectral density, we have to eliminate the dependence on t, and therefore, you would like to average this expression over one time interval, right. So, we continue to do that. So, the average value of the autocorrelation function would be integrate from minus t by 2 to plus t by 2, that is 1 capital T, and this expression, right, that is whatever is the expression that comes out to be. So, if you follow a few steps and if you expand whatever expression we had there, we would have it is 1 upon T and phi I of m would remain phi I of m, and you are going to get phi g g, which is the autocorrelation of the pulse g tau minus m times capital T. So, this is no longer a function of t, because t has been integrated out from this expression. It is dependent on tau, it is dependent on tau, and of course, phi g g, that is the autocorrelation of the pulse, is given by this particular expression, which is phi g g of tau is minus infinity to infinity g conjugate t g of t plus tau. So, this expression is t plus tau dt, right. And if we are interested in calculating the spectrum, what we have to do is you take the Fourier transform of the autocorrelation of the average autocorrelation function averaged over one time interval t, and you are going to get 1 over t g of f. So, where g of f is the Fourier transform of this, right, and phi I of f, which is the Fourier transform of the phi I of m. So, phi I f, you would write it as the expression as given here, and g of f is the Fourier transform of g t. So, this would be the typical structure of the spectrum of the low pass equivalent stochastic process, or the PSD of the low pass equivalent signal. Now, the signal we call it a stochastic process because it is being modulated by the information bearing signal. Now, what we get from this particular expression that we have over here is something very important to note, is that the PSD, that is the power spectral density of V of t, that is what we have, is dependent on the power spectral density or the frequency characteristics of the pulse shape and the frequency characteristics of the information bearing signal, right. So, we have two different parts to it, and what we can think from this is, if we have to control the characteristics of this, because this influences the PSD of phi of s, that means from this you could go to phi SS of f through the relationships which we had shown before. You can clearly see that you have a choice to work with the pulse shape, which would result in certain spectral characteristics, as well as you have a choice to work with the information bearing signal. Try to do something with that, so that you get a desired characteristics. So, we would like to conclude this particular lecture here, and like to summarize that what we arrived at the end of this particular discussion is the relationship which connects the power spectral density of the low pass equivalent signal to that of the pulse shape and the information bearing signal, which in turn means that if I have to control the characteristics of the outgoing signal, I can either control the pulse shape or the spectral characteristics of the pulse, or I can do something with the information bearing signal. Thank you.